Rotary Position Embedding, or RoPE, has become a cornerstone of modern transformer architectures. Whether we're talking about large language models, vision transformers, or 3D generative models, RoPE is the industry standard for encoding positional information. But while the mathematical theory behind RoPE is elegant, the actual hardware implementation is often surprisingly inefficient. If you look at the standard implementation of RoPE, it relies on a series of vector-level operations, splitting the input, rotating the vectors, and then merging them back together. On paper, this is fine. But in practice, these split and merge operations introduce significant computational overhead that is often overlooked because we spend so much time optimizing the attention kernel itself. To put this in perspective, profiling of a video generation model on Ascend 910B hardware shows that vector operations account for about 22.5% of the total computation. And of those vector operations, RoPE alone contributes 44%. This is a massive bottleneck. The inefficiency comes from three main areas. First, split operations, like interleaving dimensions, are hardware unfriendly on many NPUs. Second, when you move to 2D or 3D RoPE for images and video, you introduce even more layers of splitting and merging. Finally, in 3D settings, the feature dimensions often become uneven after splitting. For example, a dimension of 128 might split into 44, 44, and 40. This destroys hardware utilization. This is where RoME comes in. RoME stands for Rotary Matrix Position Embedding. It is a mathematically equivalent reformulation of RoPE that replaces these clunky vector operations with unified matrix transformations. To understand why this works, let's look at the standard RoPE process. Normally, you take a feature vector, split it into pairs, rotate those pairs by an angle based on their position, and merge them. RoME realizes that these split, rotate, merge steps can be expressed as a single linear transformation. Instead of slicing the tensor, we can use a structured rotation matrix, M for an interleave implementation. M is a block diagonal matrix composed of two x2 rotation generators. For a half implementation, it's a different structured matrix. By substituting this into the RoPE formula, we transform the process into a parameterized orthogonal transformation. This shift provides three major advantages. First, it completely eliminates slicing overhead. We replace multiple chunk and cat operations with a single matrix multiplication, which avoids memory fragmentation. Second, it allows for much better parallelization, because the structure of the matrix leverages batched matrix multiplication. Third, it gives us mathematical clarity, making it much easier to extend RoPE to higher dimensions. When we move to 2D or 3D sequences, like in video models, standard RoPE applies rotations independently along the temporal, height, and width axes. This means multiple rounds of slicing and reshaping. RoME simplifies this by constructing a single block diagonal matrix that combines the rotation matrices for all dimensions. This allows us to apply all rotations simultaneously through one matrix multiplication, regardless of whether the dimensions are evenly divisible. But the optimization doesn't stop at the math. RoME implements a fused operator design. The sequence of element-wise multiplication, addition, and multiplication is fused into a single composite operator. Furthermore, RoME leverages a cube-vector coparallel computation strategy. On modern NPUs, matrix multiplications are handled by the cube units, while the fused element-wise operations run on the vector units. By scheduling these to run in parallel, we maximize hardware utilization. The results of this approach are substantial. In operator-level tests, RoME achieves up to a 3x speedup over original RoPE implementations and a 1.48x speedup over already fused operators. When integrated into full models, we see an overall inference speedup between 3% and 10% across various tasks, including Llama 3.1, InternVL, and Flux. Even in training, RoME provides a clear benefit, with end-to-end improvements in throughput for models like WAN 2.2. If we look at the complexity, both standard RoPE and RoME have an arithmetic complexity of O, SD, where S is sequence length and D is dimension. However, the hidden cost of standard RoPE is the memory I/O and the number of kernel launches. By moving to a matrix-based formulation, RoME reduces the number of kernel launches from several operations down to a single fused operator. Essentially, RoME takes the complexity of RoPE implementation, which can sometimes span thousands of lines of code across different variants, and collapses it into about 100 lines of clean, matrix-based logic. By shifting the focus from data movement to structured matrix operations, RoME removes the primary bottlenecks of positional embedding. This not only speeds up current models, but opens the door for more efficient scaling in long-context video generation and complex 3D scene understanding.